Hi there, and welcome to our lecture on compounds and molecules. This will be reaction 1 of Unit 4. Our key ideas: what holds a compound together, how can the structure of a chemical compound be shown, and what determines the properties of a compound. So we're going to start looking at this first question: what holds a compound together? The force that holds atoms or ions together is called a chemical bond. So that's one of your vocab terms. Chemical bond is the attractive force that holds atoms or ions together. Typically, we can show chemical bonds or compounds in different ways. We've got different models that we have used. We've got a ball and stick model in the top left here. We've got a space-filling model. We've got a structural model. And we've got the chemical formula for this particular compound. And typically we show bonds, or these chemical bonds, with little sticks, and we'll talk about here in just a little bit that the stick method is good for showing what kind of bonds we have, but it's not necessarily that accurate because these solid stick-like structures don't exist. So it's just kind of a visual for us to see that those particular elements are bonded together. Alright, next question. How can the structure of a chemical compound be shown? So the structure of a chemical compound can be shown by various models. Different models show different aspects of compounds. So we can start with the chemical structure, which is just the arrangement of atoms in a substance. Some models represent bond lengths and angles. A bond length is just the distance that is between the nuclei of two bonded atoms, and typically is an average because it will fluctuate and differ slightly depending on what kind of compound we have, and other surrounding elements can affect it too. The bond angle is the angle formed by two bonds to the same atom. So an example here, technically water, we've got oxygen bonded to two hydrogens, makes a kind of a bent shape. So the angle that's between these two hydrogens, this is an angle here, and this is just a bond angle. What kind of angle is made because of the way these atoms interact with each other? The reason water bends like this, and this is called a bent representation, is we've got these electrons that favor this outer position, and they're found in pairs outside the oxygen atom, which causes the hydrogens to bend or move towards each other. So this is actually the formation of water. So an example here, just kind of give you a visual. The bond length is the distance between the nuclei. So we've got two hydrogen atoms, and what the distance is between these two. And when hydrogen is bonded to hydrogen, it's going to be an average of 75 picometers, which is an extremely small measurement. Okay, so the first representation that I showed you on the previous slide, or one of the previous slides, was the ball and stick model. The atoms are represented by balls. The bonds that hold the atoms together are represented by sticks. And here we've got the bond length and bond angles represented as well. So for that water molecule, that angle was 104.45 roughly degrees from hydrogen to hydrogen. And we can do 360 minus 140 if you really wanted the outside angle, but we're not going to worry about that. So again, these sticks are there to represent that the oxygen and hydrogen have a bond, or they're sharing, or they're donating, but there's a connection between them, and we'll talk about whether it's a covalent or ionic bond in the next lecture. And structural formulas, the chemical symbols are used to represent the atoms. So instead of the balls here with the letters in the middle, we can save some time by just writing the element symbol. So O for oxygen, H for the hydrogen. Still showing the bond angle here, well, sort of representing it, not necessarily keeping it specific, but we're showing that it is a bent molecule, and we're just using the element symbols. We also have a space filling model, and this represents the space that's occupied by those atoms. So, for example, oxygen technically takes up a lot more space than hydrogen does, so we show it as kind of a sphere, and then we squish two smaller spheres to represent the hydrogens up against that oxygen atom. And when we look at bonds and we show them in this ball and stick model as very rigid and structural, we want to see those as being able to be bent. We can stretch those, we can rotate those, and they don't break because they're technically not a solid rigid structure. So a better representation of bonding between, let's say, hydrogen and oxygen might be better represented by a spring, because we can bend those, we can stretch, we can compress the springs, we can bend the springs. This kind of shows a better idea of how that bond can actually act and behave. Again, a spring is a physical item that's connecting the two atoms, which really doesn't exist either. Overall bonding is just an attraction between these two atoms. Again, we'll talk about that in the next lecture. Most bond lengths are average distances, so they're not exact, and then these bonds are going to hold these atoms together very tightly. Our next question, what determines the properties of a compound? So the chemical structure of a compound is going to determine how the properties of that compound are. So looking at the compounds, we've got something called a network structure. These are strong solids, so if we look at something like quartz, which is SiO2, or silicon dioxide, it's made of silicon. We've got one silicon atom, and we've got two oxygen atoms that are bonded together. And when these bond together, they bond in a strong, rigid structure. Some networks are made of bonded ions, so we've got ions that are attracted to each other, positive ions or negative ions are attracted. So these attractions between opposite charges give the ionic compounds very high melting points and high boiling points because of the ionic interaction. So if we look at table salt or sodium chloride, it's typically made of this tightly packed repeating network of positive sodium ions and negative chlorine ions. I thought I had a visual, but we've got these positive ions and negative ions that are tightly packed together, forms kind of a network. So we can kind of get this crystal structure, so we might see it as, say we've got a cube of salt here. Well, within the cube of salt, we've got not hydrogen, but we've got, say, sodium and chlorine, and then we've got another sodium and chlorine, or actually it'd be opposite, chlorine, sodium, and then sodium, chlorine, that are kind of bonded together in this structural, and this would repeat all over this salt cube. Alright, some compounds are made of molecules. They can be solid, they can be liquid or gas. The strength of attraction between molecules will vary. We've got an attraction between water molecules that we refer to as hydrogen bonds. Very weak attraction between each other, but it's the positive charge that is found on the hydrogens and the negative charge that's found on the oxygen tend to be bonded to another water molecule. Here's a note here: hydrogen bonds are not as strong as the bonds holding oxygen and hydrogen atoms together that are within the molecule. So I do have a visual of this. So the bond that's between this oxygen and the bond that's in the hydrogen, so between oxygen and hydrogen, it's a very strong bond. We've kind of drawn some dashed lines in here. These are referred to as hydrogen bonds. They're very weak attractions, technically not even a bond, but because of a partial positive charge, because hydrogen tends to be a little more positive and oxygen tends to be a little more negative, the positive charge on a hydrogen atom is going to be attracted to the negative charge of an oxygen atom on a corresponding
page lemon
on a corresponding water molecule, the oxygen of a corresponding water molecule. So we've got this attraction. So this refers to, or this makes water very polar, so it kind of adds some behavior to water. For example, if you have a running stream of water in your sink and you bring a charged particle or charged substance up to it, you'll see that the stream of water will actually move towards or away from that object depending on what the charge on that object is. Kind of an interesting phenomenon. So that's all I have. Thanks for listening.